Morning, dear students. This session will talk about three-dimensional stress-strain relation, which is other way called as generalized Hooke's law. Okay, you know Hooke's law. It says the stress is proportional to strain, which we have learned in strength of materials. Okay, right. So that we will derive in three-dimensional. Okay. So for that, let us consider a bar. Okay, of some cross section. Okay. Right. Let us say this bar is acted upon by a stress called sigma x. Okay. Right. Okay. Now, say this is dimension L. Say this is B. Let's say this is D. Okay. Yeah. So due to stress sigma x in x direction. Okay. So let it be x, y, z. Okay. Due to stress in x direction, what are the strains? Okay, what are the strains that you have in this body? Okay, so let us write strain in x direction. Okay, as stress is acting in x direction, it is stress by Young's modulus. Okay, this is strain in x. Okay, do you have strain in y direction? Yes. Okay, how it is possible without stress? There is strain possible in y direction also. That is because of Poisson's effect. Okay, what is that called? Poisson's effect. Okay, so because of Poisson's effect, there is a strain in y, also strain in z. Though there is no stress in z direction, you have strain because of Poisson's effect. Okay, so what Poisson's effect says, the Poisson's ratio is equal to lateral strain by longitudinal strain. So if this is the stress direction, we say this is longitudinal. Okay, the other directions are lateral. Okay, so now what we want is strain in y direction. So which is nothing but the Poisson's ratio, which is called nu, into epsilon x. Yeah, epsilon x is nothing but sigma x by e. So nu into sigma x by e is the strain in y direction. Yeah, when you talk about the nature or the sense, this is trying to elongate the dimension L. So we say it is tensile. So as this dimension elongates, B and D are trying to reduce. Okay, so that is opposite. Okay, so we need to give negative sign. Okay, similarly, the other direction z. Okay, so divided by longitudinal strain, lateral strain to the longitudinal strain ratio. So now I want the strain in z direction, so which gives me like this, again adding negative sign. Okay, right. So now you see these are the strains because of stress in x direction, because of sigma x. You have strain in x direction, you have strain in y direction, and you have strain in z direction. Okay, so let us write all put together at one place. So now I have, because of sigma x by e, strain in y is minus nu sigma x by e and minus sigma x by e. So these are the strains in all three directions. Let us say similarly, you can estimate the other directions also. Let us say there is stress in y, so we have got epsilon y as sigma y by e, because this becomes longitudinal now. The other two directions will become lateral. So now the lateral is epsilon x. So it is minus sigma y by e, and the z is now lateral minus mu sigma y by e. So now you see which is called as longitudinal, which is called as lateral. Longitudinal means the direction of the stress which is acting, okay, corresponding to the strain you are calculating, okay. Now because of sigma z, then now epsilon z will be your longitudinal strain, okay, z by e. The other two directions will become lateral now, and you need to add negative sign because of compression, okay. It is sigma z by e y minus mu sigma z by e. Now these are the 9 quantities of strains because of 3 quantities of stresses, okay. Yeah, now imagine all are acting at a time simultaneously, okay. Now what will be the strain in x direction because of all stresses, like all the stresses? For example, sigma x, sigma y, sigma z, all are acting now. Now what will be epsilon x? Okay. Now this, because of sigma x, epsilon x is sigma x by e. Because of sigma y, epsilon x is minus mu sigma y by e. Because of sigma z, the epsilon x is this minus mu sigma z by. So this is strain in x direction because of all three stresses. Okay. Yeah. Now we'll continue deriving the relation between stress and strain from this expression. Yeah. All other three you can write it. I'll write it here itself. Sigma y by e minus mu sigma x by e minus mu sigma z by e. Okay. Then epsilon z is equal to sigma z by e minus mu x by e mu y by e. Okay. Yeah. So let us consider the first relation to develop the stress strain relation. So I am considering epsilon x is equal to sigma x by e minus mu sigma y by e minus mu sigma z by e. Okay. Yeah. Now let us take, just rearrange the terms here. 1 by e. Okay. Sigma x minus mu common from these two. So I'll have y plus z, sigma y plus sigma z. Okay. Yeah. So this is the expression that I get. Okay. Yeah. Now let you know from the basic strength of materials concept that the sum of the normal stresses is a constant. So let us give a symbol like capital theta. Okay. So the sum of all three normal stresses acting on a body is constant. So this that constant, let it be theta. Okay. Now from this I need the sigma y plus sigma z. Okay. So sigma y plus sigma z will become minus sigma x, theta minus sigma x. Okay. Let us substitute this into this epsilon x 1 by e sigma x minus mu into this one theta minus sigma x. Let us simplify 1 by e sigma x mu theta plus mu sigma x. Okay. Now again 1 by e sigma x minus, okay, sigma x terms you just combine. Okay. So it is sigma x plus mu sigma x minus mu theta, just separate it out. Okay. Now if you see 1 by sigma x into 1 plus nu minus nu theta. Okay, right? Now separate this sigma x. Okay, so epsilon x e goes to left hand side is equal to sigma x into 1 plus nu. This goes to the left hand side. So it will be nu theta. Okay, plus. So now sigma x will be, okay, nu theta by 1 plus nu plus e epsilon x divided by 1 plus nu. Okay, so this is sigma x expression, wherein you see there is theta involved, which is again nothing but sigma x plus sigma y plus sigma z. So to calculate sigma x, you have again unknowns on the right hand side. Except this theta, all are known values like Poisson's ratio, Young's modulus are all material property, and strain in x can be get from the strain displacement relation. Okay, and again displacements are from finite element method, which we get. Okay, so to get sigma x, you need theta to be substituted in terms of non-quantities. Okay, so to get it, we take volumetric strain, volumetric strain constant. Volumetric strain is calculated from the basic strength of materials, that you know that epsilon x plus y plus z. Okay, you have got expressions for these in terms of stresses. You just substitute them, is equal to epsilon x. You just look at here, epsilon x is written, okay, here sigma x by e minus nu y by e minus nu z by e. Okay, so that you substitute it here, x by e nu y by e nu z by e. Okay, this is epsilon x plus epsilon y, y by e x by e nu z by e, plus third one sigma z by e minus nu x by e minus nu y by e. Okay, now you just pick out the common terms, like sigma x is here, sigma x is here, sigma x is here. So just combine those terms. Okay, so what we have here is volumetric strain is equal to, I'm taking sigma x common. Okay, let us say sigma x by e common. Okay, so this will be 1. Here you see minus nu, again minus nu. Same way, y by e common, 1 minus nu minus nu. Z by e common, 1 minus nu minus nu. Okay, right? Now simplify sigma x by e, 1 minus 2 nu, y by e 1 minus 2 nu, z by e 1 minus 2 nu. Yeah, you see all the terms have got 1 minus 2 nu by e common. Okay, so pick it out. The remaining are x plus y plus z. Now what you can write for this? 1 minus 2 nu by e, that is theta. Okay, so now what is theta? Because we want to substitute for theta, right? So this goes to left hand side. So e by 1 minus 2 into epsilon v, the volumetric strain, is equal to theta. Okay, so this you need to substitute here. Okay, this expression. See, so that we will write it here. Sigma x is equal to nu theta by 1 plus nu taking sigma x nu theta by 1 plus nu, okay, plus e epsilon x by 1 plus nu, e epsilon x by 1 plus. So substituting this theta in this expression, okay, nu by 1 plus is already there, e epsilon v divided by 1 minus 2 nu into this theta, okay, we have got substituted, plus other expression need to be written as it is, okay. Yeah, now you see sigma x is written in terms of these quantities, which are all either material properties or can be measured, okay. You see epsilon x or the epsilon v, like epsilon x plus y plus z, okay, all are measurable, okay, and capital E and Poisson's ratio are the material property, okay. Yeah, now you can still simplify this by standard notation, okay. We call this expression as lambda into epsilon v, plus we get this expression reduced from shear modulus, where shear modulus says, I'll write it here itself, like E is equal to 2g into 1 plus nu. This was the relation that you have developed in your strength of materials. Okay, now for E divided by 1 plus nu, what we write? It is 2g. So now you can write 2g here, right? Into epsilon x. So this is the most simplified form of stress strain relation, that is other way called as generalized Hooke's law. Yeah, the other stresses also you can develop in the similar manner, plus g epsilon y plus g epsilon z. So these things are to be similarly done as what we have done for sigma x. Okay, this is what is called generalized Hooke's law. Okay, and what are these lambda and g called? They are nothing but Lamis constants. Okay, Lamis constant. Okay, though we call this as a shear modulus. Okay, and it is also called as Lamis constant along with the lambda. Okay, so there are two Lamis constants, which are lambda and g, which are involved in the generalized Hooke's law. Nothing but three-dimensional stress strain relation. Okay, thank you.